So welcome, Michael Burr from Clemson University. He'll speak on complexity estimates using continuous amortization. Okay.
Well, thank you for the invitation. I noticed that the title is probably different than whatever was posted because I took, I copied the slides and I changed all the internal ones, but I think I forgot to change the title page. All right, so this talk is going to have two parts. Oh, no, I'm going to have the introduction first. All right, so let's start with a polynomial. So this is going to be our polynomial. And say we have an algorithm that computes this. So this is meant to be an approximation to the smooth curve. So this is some piecewise linear approximation, and the actual curve is that. And this is the real point of this variety. All right, and this is done by taking a domain and dividing it and subdividing it. So if you look here, we started with a big square. It gets split in half and gets split in half or in quarters and quarters again and again. There's small boxes here. There's large boxes over here. It all depends on how difficult it is near each point. So the problem is, the general problem that I want you to think about at first here, we're going to step back from this as we go and then come back to this one, is we want to relate the number of boxes to the geometry. How does the geometry affect how fine the subdivision is locally? Okay, and so the algorithm that I'm showing here is called the PV algorithm. All right, so for approximating varieties, there's lots of different algorithms. You have, for univariate polynomials, there's a list and it goes on and on and on. And for multivariate polynomials, there's another list and it goes on and on and on. And so applications is you can use these subdivision type techniques for many different problems, and there's just a list of problems that some of which I found by Googling and all sorts of different some I know about, but there's a whole bunch here of just the approach of subdividing an input domain into smaller and smaller pieces shows up in many, many different situations. And that's what we're going to be looking at. So the first part of this talk is part of a sales pitch. I want to tell you about continuous amortization. So this is a technique for analyzing the complexity of subdivision-based algorithms, and this is meant to be more general, more accessible. The second part of the talk will get a little more technical, but that's how it goes. So we saw that picture at the very beginning. Let's bring it, that was a two-dimensional problem. Let's bring it down to one dimension. Let's say that we want to isolate the roots of a univariate polynomial. So f is going to have, say, integer coefficients, and we have our initial interval, and we want to split it up into pieces. Each piece either has one root or no roots. Okay, so Wilkinson 5 has roots at 1 through 5, and the interval is 0 to 7. So say I break it up like this. Each of the vertical bars represents the edge of a sub-piece that I've broken it up into. And each sub-interval has either one root or no roots. You'll notice that there's more intervals than are strictly necessary. That's important because we're going to have to deal with that later. But the idea is you're breaking it up. On each piece, there's something easy to understand that's going on, and you want to count how many pieces do you get. Okay. So continuing with this prototypical example, say we had interval I, and we do some test on it, and this test comes back false, and we subdivide it. We get a left and a right side. Okay. On the left side, say we test that, it comes back true. We don't do anything more to it, but the right side comes back false, so then we have to subdivide that one again. And then we keep going, maybe that one needs to be subdivided, and then a bunch more subdivisions, and then at the end of the day, you've got this interval, and it's been broken up into various pieces. Some things to note is that the subdivision is not uniform. You've got some places where you've got really big intervals, and some places that are really small intervals, and that matters. Okay, so what are some complexity questions? Well, how much work does it do? It's not doing a uniform amount of work locally. Some places are big, some places you need a lot of subdivisions to deal with. So how many subdivisions actually happen? And what are other things you might want to be interested in, like the bit complexity or things like that? All right, so what are the challenges here? It's an adaptive algorithm. That's what I've been focusing on with that the intervals are different sizes. You've got, if you look at the subdivision tree, sometimes you'll have a really shallow part of the subdivision tree, sometimes it'll be deep. And you want your analysis to take care of that. If you were to just look at the maximum depth of a tree, you get the complexity, but it's going to be way larger than what you want. It's going to have way more, it's going to be a huge overcount. And what the underlying thing that I'm going to keep coming back to is we want some connection to the intrinsic geometry. We want to express our answer in terms of geometry. So just to put this in context, subdivision-based algorithms, there are previous work. So some algorithms, some analyses, what they do is they look at the subdivision tree and they get bounds on the width of the tree at every level, add it up over the height of the tree, and you can get the total count of the number of nodes. All right, so depth of the tree. So what you can do is you can say, okay, the tree's got a few deep paths, and you can charge the cost of subdividing to those few deep paths and amortize the cost that way. Okay? There's condition number approaches, and those will use the condition number to say how bad the problem is, at least locally or perhaps globally. All right, and so these are all different ways of approaching analyzing subdivision-based algorithms. The method I'm going to present, continuous amortization, at least in this first part, can be used for all of these different techniques, and it sort of subsumes all of them. Okay, so continuous amortization is a unifying technique for studying the complexity of these types of algorithms. All right, so I'm going to generalize what we've had so far. So instead of like looking for roots, let's just say we have an interval and a test. Doesn't matter what we're testing for, we're just doing it a little more abstractly. And what we want to do is we want to recursively bisect our interval until our test works on each subinterval. Okay, so it doesn't matter, before I showed you a picture where we were finding roots, it's just sort of a general framework of you just want to bisect until some test is always true. Okay, so the trick here is to define a function called a local size bound. So a local size bound is a function so that has this property. At a point, the value of the function is less than the smallest, the width of the smallest non-terminal interval containing x. So it's easiest to see this through a picture. All right, so there's the definition, but a picture is going to help. So that's just the same definition. All right, so we've got this point x, and we've got all the possible we have all sorts of possible intervals. Some of them, well, so then we're going to look at their values. On our test, some of them come out to be true, some of them come out to be false. All right, but we only are going to care about the red ones. So now let's go through this carefully. All right, we're taking infimum over intervals that contain our point x. J3 doesn't contain our point x, doesn't matter. Throw it out. We ignore it. We want the test to be false. J2, the test is true. We ignore it. Okay, so what we're left with is only the intervals that contain our point x and are false. And our f has to be less than the smallest of those. So of these three, the smallest is J4, so our f is going to have to be less than J4. Perhaps it's even smaller because these are only 5 intervals, and maybe there's another one that I forgot to draw. You don't have to be centered, it can be off-center. It's just sort of a local test of, at this point, what's the worst interval at this point? How big could that be at this point? Okay, that's the thought process. So our f of x is smaller than the worst thing that could possibly happen at x. That's the idea. All right, so some properties of this. Notice it does not depend on the input interval. It's not saying the intervals that you get from subdivision or anything like that. It's just saying, okay, what's the worst that can happen at x? What's the smallest interval that has to be subdivided at x? All right, it's sort of a local worst case analysis. It's saying what's the worst that can happen at x. We're not going to compute f. We're not going to compute the left-hand side, the right-hand side. We may write them down, but we're going to approximate them at the end of the day so that we don't have to, because they can be complicated. So a couple things. If we have an interval that's non-terminal, if we have something that's subdivided, its width, by definition, has to be bigger than f of x. So it's sort of a lower bound on something that has to be subdivided. And you actually can get a bound on the local depth of the tree. So if you look at the subdivision tree and you find out which leaf has x, and you look at its depth in the tree, that's a bound on it. Okay? So these are meant to sort of justify and see how f fits into the picture that we're building. And feel free to interrupt me if you have any questions at any time. Yeah.
Just on, suppose from your presentation that C is such that infimum really exists, so like there's, if I make them smaller and smaller, these intervals at some point C has to be true, and then intervals or something like that. Right?
Well, if you could subdivide, if C could be false forever, then there's no guarantee your algorithm will terminate.
Yeah.
So locally, there should be the infimum should exist. That would be the hope. I will put a caveat on that. You don't need it. You can avoid it on a measure zero subset. So you could have it. This could be zero on a measure zero subset if you're careful about that.
Okay.
I will try towards the end of the section. I will tell you an example where this happens. But if I forget to, remind me before I get to part 2. Yeah.
So in this consideration, do you always assume that the computation is precise? So for example, do you consider the case when the Cj is false even when J contains the root?
Yep.
Or the
So it's a soft test. It could fail for the wrong reasons. I mean, it could say false when it really, if it were ideal, it could say true. That's okay. Okay, but the f is going to reflect that. So if it says false when it really should say true, f's going to be smaller than that, even though the answer wasn't right. Okay. So what's the big theorem is that if you can define a function f, then there's a bound on the number of intervals in the final partition. You integrate 2 over f, add 1 just to be safe in case you don't subdivide at all, and that's a bound on the count of the intervals in the final partition. So that's the idea, is that to get a count, we're going to integrate this local size bound, and that local size, and by integrating that, well, we're going to get our values that we want. So that's sort of how it all gets connected. So the sketch of the proof is the integral over each terminal interval is at least 1. It's easier to see this in a picture. So going back to that first picture we had, all right, we have a bunch of intervals, and we're just going to add 1 for each interval, and you add them up and you get k. Well, the number of subdivisions plus 1, so that k is equal to, let's do something silly, the width of the interval divided by the width of the interval, which is 1. Okay? Now that's the same as integrating over the interval, but this, if you look at this is bounded by that integral that I had on the previous slide. Okay? So that integral of the local size bound shows up here. And you can also show that for each of the intervals, the value of the integral is at least 1, so you're getting at least 1 for each piece, and you add it up, and you get at least k. So that's, the proof's nothing fancy, but it works quite well. All right, so let's do an example on the ideal problem. So a Sturm sequence will give you perfect information. So let's start just to make it all easy. We're going to start with a square-free polynomial. Don't really need it, but it's easier for thinking about for that. All right, so Sturm's test will tell you exactly how many roots. If you've got 0 or 1, you don't subdivide. If you've got more, you subdivide. Okay? So let's think about x. What's a local size bound for x? Okay, so what would it mean that an interval has to be subdivided? An interval is subdivided if it's got 2 roots. When does it have two roots? Okay, so it could be an interval that has two roots to the left. Left. All right? It could be that it sort of has a root to the left and a root to the right, or it could have two roots to the right. I got my lefts and rights correct from your perspective, right? Okay, so if you just imagine for a moment, I'm sure you can come up with various situations where one of these is best, or one of these is smallest. So you could sort of have both roots on the left crowded together right near our query point x and everything else to the right spread out, or we could have alpha 2 and alpha 3 close to x, or anything like that. So how do we get a lower bound on the size of an interval that has two roots? Well, if it has two roots, then you've got a closer root and a further root. And that further root is at least as far as the second closest root to x. So you can actually bound it by saying, well, that was too complicated. There were too many cases. Instead, what I'm going to do is I'm going to say, all right, if I've got two roots, I have to have a close one and a far one. The smallest case is where I have the closest one and the second closest root. But in general, I could just have a close root and a further root, and that further root is at least as close as the second closest root. That makes sense? The second root in the interval is further away than the second closest root to x, because it's a subset, because it's more restrictive. So this is the bound that we're going to use. We're going to say, well, if our interval is subdivided, if we've got two roots, then what has to happen is it has to be big enough to contain the second closest root. That's what this is saying. And now we integrate it. So we're just taking that, the theorem that I had before, this is a slightly different version of it. I said max instead of 1 plus, but it's the same theorem. And if you evaluate this integral, it takes a little bit of count 1. You get this. Now let's go through what this says. Okay, so this is a statement in terms of roots and a few endpoints of our interval at a constant. So this is a bound of the number of subdivisions you've got. You've got things like distances between roots. You've got distances between roots and endpoints, distances between roots and endpoints. It's a very geometric answer. Okay, so what we're getting is the complexity in terms of the geometry of where the roots are. So this is a count on the number of intervals. Tells you exactly how many. All right. If you use Mahler-Davenport, you can get that this is dl plus lnd, which matches the best known complexities for the number of subdivisions that you're going to get. D is the degree and L is the log. So this is a geometric answer, but it also matches what's best known. So that's what I mean by I want to measure the complexity in terms of the geometry, is I want to express the complexity of this in terms of some geometric information that I'm dealing with. All right. So this is a technique that works on many, many different algorithms. For Sturm sequences, matches the best known. Descartes rule of signs, best known. Square free eval improves upon the best known. Same technique, just change your local size bound. Okay, just for the Descartes rule of signs, it's based on that 1 and 2 circle test. You twist that into a local size bound, and you've got a complexity bound. The square free eval is a little more complicated. All the complexities are expressed geometrically as distances between roots. Okay. Let's make it a little more complicated. So how can we generalize? Okay, so I'll make it as general as I can. I'm going to start with a measure space, and S is just going to be a collection of finite measure subsets of X of some type. All right. So I'm going to have a test. My stopping criterion is that it's a test from my set of finite measure subsets, whatever subsets I deem appropriate, to true false. I'm going to start with some initial region. and I'm going to recursively subdivide, just like we did before, but instead of doing the first example I showed you was splitting a region into 4 pieces, or I could bisect this, I don't care. Just break it up into pieces. At least every time I replace a region with smaller regions, at least 2 of them, and they partition it. So I take my region, I can break it up any way I want, just as long as it's all of those things that I break it up into are subsets of X, are in that S. Okay. So we can also get a local size bound. It's the same definition. Well, a little different, but nothing big. Okay, so instead of the width, I'm going to use the measure. I'm going to say that J has to be in the set of objects that I'm allowed to use. So instead of interval, my region has to be an allowable region, has to contain X, and has to be false on that region. Same thing, but just twisted a little. So what's the generalization of the theorem we saw before? So again, all that really doesn't matter. There's one thing that maybe matters. These last 2 lines are, we'll take a look at. But what it says is we can calculate other things using the integral that we've seen before. So we have our local size bound. All right. So this one says that when you subdivide a region, you don't get really tiny. You subdivide it subdivides fairly evenly. You don't get one region that's really small, that's really, really small. There's some bound that says, okay, if I'm going to split it into 10 regions, each has to be bigger than 1/100th of the original region. So you're not getting something, there's a lower bound on how small the subdivision can be. And this G is a non-increasing function. So forget about the non-increasing function for just a moment more. But what this says is that we can integrate something and we get we can get a count on the number of regions. But now to this non-increasing function. Why would we be interested in adding a function? Bit complexity is a great answer. Say we want to calculate bit complexity. So that's a chart. Then our G could be a bit complexity. It says, okay, for a leaf, how much did it cost to make this leaf? What was the bit complexity of creating that leaf? So what does this say is that this integral can be used not only to calculate a count, it can calculate a bit complexity or any other function that you want on the leaves of your tree. All right. So what can we do? Well, so we could, and this I should say also that because I'm saying just a general measure space, I don't need to do, I was doing 1-dimensional examples before. Doesn't matter, I can do 2-dimensional examples, 3-dimensional, any dimension. Doesn't even have to be Rn. But let's look at it for 2 dimensions where we're isolating the complex roots. For a Sturm sequence-based algorithm, that's the number of regions that you get. It's a count, just tell you, there it is. Okay, and it's also, again, these DIs are distances between roots. We get the width of the interval. This matches the best known complexity. C-eval is an evaluation-based one, based algorithm for finding complex roots. This one's based on, I believe, the 8-point test. The version I have here gives a count on the complexity of that algorithm, and this improves upon what's known. And C-eval is T and Sargov. So we can do higher dimensions. How about bit complexity? Descartes rule of signs. We can do bit complexity, matches the best known. We can do square for eval. All right, it proves upon the best known. All right, so we can, that function, that G function, we make that G function record the bit complexity. Somehow doing that, I don't want to go through the details. But the same integral works. You just have to work it out. So the expressions are long, but not too complicated. It's all Calc 1 that you have to do at the end of the day to evaluate the integral, but like square for eval, the expression is large, but the best known. That G function, instead of being like bit complexity, you could do expected time. So this is what I was going to come back to. Is I'll tell you a weird one. Okay. So this one's on the slide. So say here's a problem in algorithms. You have a fair coin and you want to simulate a biased coin. How do you do it? So the biased coin is going to have, heads with probability p, tails with probability 1 over p. So one way to do that is you start flipping the fair one and look at what binary number you get. And if the binary number is bigger than p, then you say tails. If it's less than p, you say heads. I think that's how I set it up. All right. So if you take this and you use g to be the expectation of, so how is the subdivision? Well, each time you flip a coin, you're actually throwing out half of the remaining interval. Okay, so you flip it and you get 1. That means that your number's only in half of what's left of the interval. Okay, but you can put g as the expected value of landing in a certain interval, and do this, and you'll get a value. You'll get an expected number of flips that you need. And if you do this, there's a singularity in the g function. There's one where it goes to infinity, or the g function, or 1 over, depending on how you're setting things up. But you get something that goes to infinity, but it's at one place, it's a log, it ends up being something you can integrate over. So does that more than answer your question, hopefully?
Okay, yeah, thank you.
All right. So you could do unequal size subdivision. So homotopy continuation is a very popular topic in numerical algebraic geometry right now. It's huge right now. So if you look at this paper by Bergerser and Cooper, then what you end up with is they say, if you just sort of untwist what they have, they say that for homotopy continuation, which I know you've had some speakers here who have probably have talked about this, so I'm not going to tell you what it's about, but you can think of it as dividing up your time domain. You've got an initial polynomial and your final polynomial. Each step means a step along the time domain. You're breaking your time domain up into small and large pieces. So so what it says, so if you go through their paper, what it says is that at a specific point, this is the smallest interval on T that contains your point that has to be subdivided or would not be a valid step size. All right, so if you have anything smaller than this and you contain your whatever time step you're at, that's a valid time step. You're going to be able to do your corrector method and it's all going to be okay. Now, if you use continuous amortization on it, you get this, which is exactly the bound that they got in their paper. So I'm not doing anything here except taking their result, thinking about it as subdividing my time domain, and applying continuous amortization and getting the original result. So this is the end of part 1. This is sort of the introduction. This is the selling. I'm trying to say, this is an interesting technique. It applies to many, many cases. It sort of subsumes all these other results. So it's that list of things is, I have a paper where I just go through and, match or improve the complexity of all these other papers that are, 6 or 8 different papers, and they all just one after another. You can just do the technique with a little skill, and it works. And you get either matching or better balance. And so it sort of brings together all these different ideas. So I'm going to go into part 2, but I'll pause for questions.
So here by continuous amortization, so basically you mean finding like a function to give a lower bound
A local lower bound.
on the thing we want to estimate, like the complexity, and compute the integral, and that will be the global bound.
Yes.
Why did you choose the name continuous amortization?
Because I think of the f as a charging function. The local size bound is a local charging function. So it sort of says how much work you have to do locally. And then when you integrate it, you're if you were to say divide by the width of the interval, then you're averaging it.
I think I was teaching honest algorithms at that time when we were writing that paper. So we had other names for it. That's the right name for it.
The local size bound reminds me of is a type of charging function, and so that's at least in my head where it comes from. All right, so I want to talk about higher dimensions, and this is almost ready to be published, but not yet. So I want to talk about going back to the very beginning. We had that picture of an approximation by subdividing. We were trying to get an approximation for the curve, and we were subdividing our initial domain. And we want to say, well, we want to study this. So just to hammer this home, the curve to me doesn't matter. What matters to me, I want to know the number of boxes. This is what I'm interested in. The curve, yes, we can calculate the curve. That's a different algorithm. What I'm interested in is how are the boxes. Okay. So the specific algorithm, I'm going to go through some of the details on it. So this is going to be a little more technical. So I'm going to have a polynomial, bivariate polynomial, and my box is going to be I cross j. And if I write box of a function, that means it's an interval over approximation. So something like a centered interval form or something like that. Something that's bigger, that's easier to compute, but contains the image. Okay, so the two tests are C0. C0 being true means that 0 is not in the over approximation. So this is, I'm going through planar vectors algorithm. 0 not in the box, that means the curve doesn't intersect the box. There's no value of 0 in the image because this box is an over approximation, so the curve just doesn't enter the box. We can ignore that box. If we have C1, that means that 0 is not in this. And what that says is the curve, you have the boxes of the gradients, 0 is not there. That means you've got no 2 points in the box that are perpendicular, whose gradients are perpendicular. In other words, the curve doesn't bend much. If it enters the box, it doesn't bend much. Okay. So their algorithm is as follows. You start with a box, and you subdivide it, and until on each piece you either have no curve, or the curve is fairly controlled. All right. So before I get into the continuous amortization on this, I want to adjust one of the statements. So the C1 test. So that's the C1 test. If I write it out a little bit, what it says is I compute the approximation, I compute the over approximation of the x derivative on our interval, the x derivative on the interval, multiply those together, do the same thing for the y's and add it together. The problem here is that you do operations after you do the interval calculations. And that actually messes things up. It makes things a little more complicated. So I'm going to have to replace this test by something that will still work in all their theorems, but is a little bit better for my purposes. So I'm going to deal with the function, four-dimensional function, instead of the two function, the 4-1. So it's just the gradient again, but there's no interval forms here. And what I want to do is, it still does the C1 condition, but I want to do the interval form, I want to do the box form right at the very end. So the box of the G, that's better than what they had, but it doesn't change the proofs. So I'm going to do the new C1 test, is that 0 is not in the box of I cross J, I cross J, of G, I cross J. So it's the same test. It says that there's no 2 points in the region, in the box, that have orthogonal gradients. It's just when I do my interval arithmetic is at the very end. Okay. So there's some, now let's do some geometry. Okay. So there's a univariate result that says that if you have these should be h's. Those are h's. All right. So if we have a univariate polynomial h, and we look at the ratio of and it's non-zero at x, and we look at the ratio of the kth derivative of h to h of x, it's bounded by the sum, 1 over the sum of the distances to the roots to the kth power. Okay, that's not difficult to prove. Let's make a two-dimensional version of this. So I'm going to pick a point and just pick a unit vector, any vector. That if I draw the line in that direction, it intersects the curve in a bunch of places, and I can think of this line as a one-dimensional situation. So I have all the roots of the polynomial f, but only in the direction of my vector. And then if I were to take my bivariate polynomial f and just plug in, for the calc 3 vector plus point for a line, then I have a one variable system and I can use my lemma. And I can have this sigma v being the sum of the roots, but in that particular direction. Now, if we think about this, I picked a direction, a unit vector. Unit vectors come from a sphere. Sphere is compact, so there's a maximum. Or, the maximum. So I take whatever direction gives me the worst case, and that's going to be what I call sigma f of p. So it's a geometric bound, and it says, okay, it's some vector, some direction. If I travel in that direction, that's my worst case. And it's based on 1 over the distance to the curve. Geometric. Okay. So I'll tell you a little bit about where this comes from, but I'm not going to do too much. If I go back to the C0 test, remember that was 0. The 0's not in box of f. If box of f is computed by interval arithmetic using the centered form for her function evaluation. So it's basically, you plug the intervals into a Taylor expansion. So this is a multivariate Taylor expansion. I've twisted it a little bit, but this really is, this looks like a multivariate Taylor expansion, and this is a true statement that if this inequality holds, then the curve doesn't enter the box. So I need to study that inequality. So if I compare things, if I look at the terms here, it's really close to the terms that I get if I take the derivative, the kth derivative of my function in the v direction. So just like I did before, pick a direction and look at that as a one variable problem. If I take the derivative as a one variable problem, then, and you expand it using the chain rule, you get a sum that looks kind of like this. And the previous slide that tells me that this is bounded by that quantity. All right, so therefore I've got a sum here that's bounded by this quantity, whatever that is. It's a geometric quantity. Unfortunately, it's not quite what I need. So I play with this. I use some Fourier series. I use some complex variables and Chebyshev polynomials. And you can actually get that. So here we have a sum in absolute values is less than or equal to this bound. If you do this, it's a periodic function. You can do all sorts of stuff. You can actually get the individual terms are bounded not by the right-hand side, but just some correction factor here. So it's not very difficult, but it's a little bit technical, and you just say, so you can prove that the interior here individually is bounded by this. So what does that lead to? All right, so that inequality that I had at the very end, what can I say? All right, so if the width of my box is less than or equal to this quantity, then C0 is true. That means the curve does not enter the box. So this is the width is less than or equal to some constant. Well, there's a d in here for the degree, but it's more or less some constant and the distance to the curve. So it's a geometric expression. It's a geometric quantity. If I want to do this for C1, remember we were in a 4-dimensional space, so we have 4 coordinates here. But same thing. If my width of my box is less than or equal to whatever this is, which includes a geometric expression, then C1 is true. So this is our key to the local size bound that we had before. So what's the theorem? All right, so that doesn't matter. G of x, G is defined as we had it before. The number of boxes in that algorithm that I showed you before, the one that had the curve and I divided it up, it's bounded by this. It's bounded by the integral over whatever your initial region was. You're going to have to 1 over the distance squared, 1 over a distance to a curve squared, and stuff that's more or less constant for each instance. It's a geometric expression for the number of boxes produced by the algorithm. 2 things to note about this. Or 3 things. 1, I'll remind you, it's a geometric expression. I want to stress that it's pulling out the geometry. The second thing is, this is the first complexity bound of this algorithm. Before this, no complexity bound was known. The third is 1 over the distance. This is a condition number. So now this integral is relating this original algorithm to condition numbers and conditioning. So there's a lot of structure and connections that are going on here. All right. So 10 more minutes, all right? All right. So now let's do 3 examples. So you can all wake up and just, let's do 3 examples, all right? Okay. How about this one? That polynomial, and epsilon's a real number. That has no roots. There's no zeros. Okay, so there's no curve. But so there's no real solutions. If I look at the subdivisions that I get something like that. So what's happening is, even though there's no real solutions, the complex part is affecting things. The complex part gets really close to the real part right here. I think this is with epsilon is 1 over 10 for this example. All right, so you're getting really close to, the complex part is getting really close to the real part right there. So we can actually compute all the distances in the previous slides explicitly. We can get the distance from our points to our curve. We get our distance from the points to that g function. And you actually get that the number of regions is log of the size of your initial box minus log of epsilon, which is a very nice bound. Even though there's no curve, it's still not, this does not grow too badly. So you can stare at that picture if you'd like, ladies, for just a moment. So it's the complex part that's causing this. So everything, complex matters here. What if I go to this one? Now this one is a circle. Okay, so I get this. All right. Now I could do a bigger circle, but it didn't look as good because, this one's hard to show because if I do a big circle with a big radius, I don't get many boxes because it's easy. And if I do a small circle, all you get is a little dot in the middle. So this is sort of in between. We can see that we get, some smaller and smaller things here. The distances to the function and that g function, those varieties, a little more complicated expression, not too bad. You do it again, you get log r minus log epsilon. Very nice. All right. So now, let's use, but not everything is so rosy. So let's use a product of 2 Mignot-type polynomials. Okay, so if you get this, you get solutions are vertical lines. So let's deal with the case where n equals a equals 3. So that's what we get. All right, so that's kind of hard to see. So those of you who have been to the optometrist recently will be able to see that the next one is actually, well, it looks like 2 lines. And if you've got a nice new prescription, you actually see that's 4 lines. So these blobs, to make it so you can see it, they covered each other up. But there's actually 4 lines here. There's 2 pairs of lines. There's 2 pairs of lines. Yeah, something like that. There are 2 pairs, yeah. All right. So now in this case, between those centered lines, the width of the boxes has to be at most this bound, and because otherwise you would have to have subdivided. All right, and these boxes go from top to bottom. So unfortunately, the number of boxes is at least the size of your region times that A. So that's a worse bound. or not a worse noun, but that's an unfortunate noun. But the algorithm doesn't do better than that. So I gave you 2 examples to show you that sometimes it works very nicely, and one example where, yeah, it's going to have to do some more work. But it's the algorithm itself has to do work. So the integrals that we've seen before, they're going to have to reflect that sometimes this is hard. Okay, so to summarize, subdivision algorithms, they're interesting and used in applications because they're recursive and easy to implement. They're adaptive, so they only do more work when they have to. But that makes the analysis of their complexity more challenging. And what I've been presenting is continuous amortization is a uniform way. It applies to all, I will be a mathematician, I'll quantify many different subdivision type algorithms. And it can be used to calculate all sorts of things about these algorithms, like the size of the subdivision tree. And we've seen it works in higher dimensions. We've seen it works for bit complexity. I mentioned how it works for expected values. One of the things to think about is its analysis of the algorithm directly and not the subdivision tree. So it sort of breaks the subdivision tree and the algorithm and the local complexity and breaks those 3 things into different pieces. And each of those different pieces gets processed and understood separately. The results are, well, in the cases I'm looking at, are related to the intrinsic geometry. It's saying it's measuring something about the geometry. It relates the algorithm to the geometry of the input. Okay, and that's I like that because it says, well, if the geometry is hard, then the algorithm should have difficulty. If the geometry is easy, the algorithm should not have difficulty. It makes me feel happy. It's generalized to most subdivision-based algorithms, so it doesn't have to divide it evenly. It doesn't have to do any of that. We saw for a homotopy continuation, which certainly does not divide the time domain evenly. It works. You could do this on discrete spaces if you wanted. Okay, and I'm going to leave the details to you, but you can do it because you have you could use the counting measure, and you could do a discrete loop space. If you're interested in more, this recently appeared as in November 2016 in Journal of Symbolic Computation. And I'll stop there.
What if the intrinsic geometry is not known?
I don't have to know the intrinsic geometry to know that the complexity is bounded by whatever it is. So I can say, so here's an a posteriori thing. You could run the algorithm and see it takes a while and conclude that the geometry was complicated.
For example, if I'm thinking about a stopping criterion for this subdivision algorithm,
Mm-hmm.
so I want to figure out a way to make this to determine whether the result is good enough so that we don't have to continue.
Yes.
In that case, if the intrinsic geometry is not known, there are some remedies.
You don't have to. So you don't compute f. You write out that local size bound as an abstract thing. If you were omniscient and knew what the answer was, this is what it would look like. So it's sort of an intermediate step. It never gets computed, but you use it in the middle to express the local complexity, and then when you integrate it, you replace it with something else. So like for the subdivision for finding the roots, I don't have to know where the roots are to know that I have what my function is. My function is the distance to the second closest root. It doesn't matter if I know what the roots are or not. Because after I integrate it, I'm going to get an answer that just depends on the distances between roots. And that complexity says, okay, well that's what it is in terms of the geometry. It's not, you don't have to know it. You don't have to know where the roots are to be able to say that is what the complexity is. If you know what the roots are, you could actually write it down. But you just know that it's expressible in terms of whatever the roots are.
Yes, so we can we have a guarantee.
Yes, sort of, yeah. but you don't actually have to compute what the guarantee is to use it. Yes.
So if we don't want to wait until November, do you have a preprint?
No. I mean, it's in press. It's available.
Oh, it's on press already.
Yeah,
Okay.
it's. It just got a date of November.
Oh, okay.
It's,
Okay.
so it's technically not published yet, but it has a date of
Okay, it's
November.
already.
Yeah,
Okay.
yeah.
Okay.
Does it apply to Newton methods?
I think so. I haven't worked. I have not got a local size bound for that, but I think the ideas should. Because it says what's a step size. You have to get a lower bound on how good a step size is at a certain point of how you're going to subdivide. And so there should be some connection, but I have not explored it. Thank you. Thank you. Thanks for the question.
Yes.